Assalamualaikum. Today our group want to present about a study to determine the factor influencing academic student performance. Before we continue for our presentation, let me introduce our group members. Firstly is me, Muhammad Faris Haziq Muhammad Fazil. Second is Muhammad Rizal bin Maton. And thirdly is Ezekiel Simpson Simon. Now, let's start with the introduction. So, student academic performance is a multi-phase achievement, reflect the extent to which they have achieved their educational goals. So, various factors can be used to identify a level of student performance, such as time allocated to study, time spent sleeping, practice done, and so on. So, the study aims to determine whether time allocated to study affects the student performance index. So we have a 20 observation of student, and we would like to clarify our X is our study and our Y is performance index. Now let's continue in the implementation and graph section. I would like to explain about the linear model. So the linear model, the equation of linear model is Y equals to A plus BX. So the data generate a system of linear equation with the metric representation as below. As you guys can see, our M, it have a value of A and value of X, and for the V, it have a value of Y. So for the second part, we will use the normal equation for a matrix, which is the formula is M transpose M times with V, and after that we will get the value of M transpose Y. And after we done with a normal equation, we will use the least square solution, which is the formula is V equals to M transpose M inverse times with M transpose Y. And after that, we will get the value of A is 36.55 and value of B is 3.84. So from the matrix above, the best fit linear curve is Y equals to A plus BX. Therefore, our Y is equals to 36.55 plus 3.84x. So for the last part, we will find a error vector, which is the formula is E equals to Y minus MV. So after we calculate, we will get the magnitude error for the metric is 17.20. Now we at the graph section for the linear model. So I would like to explain about best fit curve against observed data. So you guys can see the scatter plot of observed data is show a best fit curve using a linear model. So the purpose of this plot is visually assess how well a simple straight line equation can model the relationship between the two variables. So the upward slope of the red line indicates a general positive correlation as the x value increase and the y value tends to increase. But the significant vertical distance between many of the blue data points and the red line suggests that the linear model is not too tight fit and that the relationship may be weak or highly variable. Now let's move for the second graph, which is error vector against x value. So as you guys can see, the plot shown the non-random pattern with residual tending to be closer to 0 in the middle of x value, and the linear model might not be the most appropriate fit for the data, or that one or more assumption of linear regression are violated.
For the quadratic model, the general equation for this model is y equals to a plus bx plus cx squared. And when we substitute the independent and dependent variable into the equation, we get mv equals to y, which represent the matrix of the system. From the equation earlier, we can derive it to find our normal, which by using our normal equation, which is m transpose m v equals to m transpose y. And after we find it, we can get our least square solution by making it as a subject. After we get our least square solution, we can get our best fit quadratic curve equation, which is y equals to 11.7527 plus 14.9403x minus 1.0566x squared. After that, we need to calculate our error, a list of our error vector by using the equation E equals to y minus mv. And after we get the list of it, by substituting all the value inside the equation, we can find our magnitude of the error, which is 68.17. From here, there's a two graph which represent our quadratic model, which on the left side is our best fit curve against observed data, which the diamond blue point represent our actual observed data. Notice how they follow the clear trajectory. They increase rapidly, hit a peak, and they begin to decrease. The red parabolic curve in the graph of our fitted quadratic equation. This line calculates to minimize the total prediction error. Visually, the red curve follows the central trend of the blue data points quite closely. The visual fit confirms our initial hypothesis, which the data is appropriately modeled by a quadratic function, capturing the essential rise and fall relationship. On the right side, which is our error vector against x value graph, in our residual plot, the points are largely scattered randomly, which is a primarily indicator of a strong model. The error balance both above and below the zero line across the range of x values. However, if you look closely, there's a slight suggestion of a pattern, perhaps a subtle curve of grouping. This non-randomness is a minor cautionary flag. It tells us that while the quadratic model is very good, a small amount of systematic error remains, and slightly a more complex model might provide a marginal improvement.
Now, we move on for the cubic model for the data. So for this model, the general equation is y equals to a plus bx plus cx squared plus dx cubed. After substitute all the independent and dependent variable into the equation, we got mv equals to y, which represent the matrix of the system. Then, we can derive the normal system by calculate using the normal equation, which is m transpose multiplied with mv equals to m transpose y. And then, we can get least square solution by making v as a subject. Then we are able to find the equation of the best fit cubic curve, which is y equals to 0.5216 plus 23.306x plus 2.8713x squared and plus 0.1188x cubed. After that, we need to calculate the list of error vector by using the formula E equals to y minus mv. Then, we got the error magnitude of the model, which is 68.12 by using the formula. Next, this slide shows the graph for cubic model. So, on the left side, we have the cubic curve fitted to our data. As you can see that the curve follows the shape of the point quite well. It rises quickly and then levels off, which match the overall pattern in our data. And for the right side, we have error plot. Each plot shows how far the model prediction is from the real data at each x value. The errors are spread around zero, which means the model is doing a decent job. The spread is tighter than we observed for the earlier model. And this indicates that the cubic model provides a more balanced and accurate fit across the data range. And this suggests that a cubic relationship may be more appropriate for this dataset compared to linear or quadratic model.
From the three model above that we have calculated, we collected all of the error magnitude into this one table. From here, we can conclude that the cubic model has the best approximation of the relationship between hours of studies and the performance index, which this is shown by the cubic model has the smallest or the lowest value of error magnitude that we computed. So that's all from us today and this presentation. Thank you.